Section 6.5 is explaining the exponential function. So if you have an exponential function, for example, y equal to 2 to the power of x, you'll substitute few numbers and you'll get that your curve is like this. The curve tends to be very near to the x-axis. So we call that this x-axis, or y equal to 0, is the horizontal asymptote for this curve. It will always be very near to it, but it will never touch it. If you add 1 to that curve, you are shifting your curve upwards vertically يعني by 1. So instead of it will intersect here and 1, it will intersect at 2. And in that case, your horizontal asymptote will be y is equal to 1. So instead of y equal to 0, it will be y equal to 1, where your curve will be very near, but it will never touch it. So when you add 1 to the curve, you're shifting it upwards by 1. And if you remember the previous relations, for example, 2 to the power of x plus 1, you're shifting that curve 1 upwards. Minus 1, it will shift down by 1. Minus 2, it will shift down by 2. So minus or plus, it will shift up or down, same as the sign. But if you are changing your x to x plus 1 or x minus 1, x, if you're changing here, you're shifting horizontally and it will be opposite. So if it is x minus 1, it will go to the right. If it is x plus 1, it will go to the left. So here 2 to the power of x plus 2, it will go to the left by 2 units. And here 2 to the power of x minus 1, it will go to the right by 1 unit. If I multiply by my curve times 2 or times 3, so the increase will go very rapidly. So this is vertical stretching. Your curve will be, instead of going like this, it will go upwards very fast. So it will go near to the y-axis. And if you multiply it by a fraction, this increase will go a little less. So it will be like you're stretching it to that side. So it will be lower than your curve. And if the number itself is more, طبعا the increase will be more. So it will come from less to very high exponent. And if it is 1.5, let's say if it is less than 2, then the increase here, it will be a little higher, and then it will be lower once it intersects the y-axis. If a is a fraction that is less than 0 but greater than 1, so it's a positive fraction like 0.5 or 0.7, your curve will be falling. So it will go from up to down. Because when the x is more, when the x as x increases, the value of y, it will decrease. So here your curve is declining, but when the value is greater than 1, your curve will be rising like this. Let's take this as an example. He already drew for you the curve y is equal to 3 to the power of x. So this is the curve. He wants y is equal to 3 to the power of x minus 1. So this is a horizontal shift. Minus 1, so I will go right by 1. So your curve will be something like here. And 10 plus 3x, you will shift your curve upwards by 10. So this point will be here. So your horizontal asymptote will be y equal to 10. So your curve will start like this and then go upwards. And 10 plus 3x minus 1, remember the 3x minus 1 which we shifted to the right, I will take it up 10 points. So this point is going to be here. Learning point 2 is explaining the population growth. So if you have today number of people b, and he told you that in 50 years, for example, this number of people will be doubled. So in 100 years it will be again doubled, it will be 4b. So this excludes that the population at any number t years, after t years, it's equal to the initial population, which is now, times 2 to the power of t over 50. So let's take this as an example. You have a world population in 2012, it was 7 billion. Use this model. What would be the population in 2212, 2212. So this minus this is 200 years. So he's asking you what is the population after 200 years. So here your number now is 7 billion times 2 to the power of t. T here is 200 over 50, and then calculate, it will be 112 billion people. Then in the second part, he's asking, assume what would be the number in 1712. In 1712 means it is 300 years ago. So this is minus, so here t is in minus, like minus 300. So your formula is going to be 7 billion, which is your number of people now, times 2 to the power of minus 300, because you're going backwards with time, over 50. Then it will be approximately 0.11 billion. Take this activity so to practice it. The population of Canada doubles every 70 years. Doubles every 70 years. So this number will be 2 because it doubles, and every 70 years, so this number, instead of 50 here, I will put 70. If the population in Canada in 2012 was 35 million, then what would be the population in 2222? So 2222 minus 2012 is 200 years. So he's asking t is 200 years. So my formula will be the population on this year will equal to the initial population, which is 35 million, times, he says double, so it's 2. If you say triple, it will be 3. Every 70 years, so the time is 210 years. Every 70 years it is doubled. Okay, so this is your formula, and you will calculate, you will get your answer as 280 million. Part 2, a certain type of bacteria divides every 20 minutes to produce 2 bacteria. طبعا this is very tricky. Divides to produce 2 bacteria means it is doubled. So it is one bacteria, it will split into 2. So it is doubled every 20 minutes. If a certain colony started with 20 bacteria, how many will be there in a colony after 10 hours? So it is doubled, so here you have 2. You started with 20 bacteria, so your B is equal to 20. And divides every 20 minutes, so you'll put here 20. And he wants after 10 hours. 10 hours, you have to convert it to minutes, because you put here 20 minutes, so this should be in minutes. So 10 hours in minutes is 600. So this is going to be your formula for the bacteria after 10 hours. You calculate and you'll get the answer. This is called the radioactive decay. Radioactive decay, here you are decreasing with time, not increasing with time. So it is given by this rule, Qt is equal to Q0 times e to the power of RT. So Q0 is the amount represented initially. T is the time passed from the initial time. So this is the initial time, this is after T times. R is the rate at which the material is decaying. Let's say it's decaying by half, it's decaying by 30%, like that. Then the half-life of a radioactive substance is the time it takes for an amount of this substance to reduce to half of its present size. So this is the formula we're going to use. Let's solve this example as a practice for this rule. So the amount of this substance presented at any time is reduced to half of its size in 13 days. What would 100 milligram of this material be reduced in 7 days? First, I need to get the decaying rate R. I need to get the decaying rate. Type. He told you that the amount is it's reduced to half in 13 days. So after 13 days, this amount, the Q final, will be half. So it will be half the initial amount. So here I have my initial amount, e to the power of minus r, and what is the time it takes to reduce to half? So 13 days, so t is 13. So the final amount is half, then the initial amount, e to the power of minus the decaying rate times 13, which is the time. So this will go with this. First you will take ln. Ln is the opposite of the exponential. So same what you're doing radical. When you square, the square will cancel the radical. So ln is the opposite of the exponential. So here I will take ln half, اللي هو 0.5, is equal to, the exponential will go minus r times 13. Using calculator, ln half, so this is equal to minus 13 times r, so I will divide by minus 13. So this is your decaying rate, 0.533190, or let's say 0.53319. So here, what he wants, he said, what would 100 milligram of this material in 7 days? So 100 milligram is the initial. So طبعا he wants after 7 days. So Q7. Initial is 100 milligram. E to the power of minus R, which is this number, times T, which is 7 days. After 7 days. So I will multiply this times minus 7. And then E, this number, times 100. So this will be the amount after 7 days, 68.85. If you want rounded, so it will be 69. So initially you need to get the decaying rate R, then you see what he wants. Example 6. Suppose that 1 kilogram of radium 101 is reduced to 0.81. So 1 kilogram is the initial, so I can put here Q initial is 1. And it became 0.81 after 1 year. So it became 0.81 and the time is 1 year. So E to the power of minus R times 1, so minus R. So every time you need to get the depreciation factor first. So I need to get R first. So solving this for the R, you will get that the R is equal to where it is here, 0.21. So my depreciation factor R is equal to 0.21. Okay, then he's asking part A, what is the half-life of the radium? Half-life means the final quantity will be half, so half the Q initial is equal to Q initial E to the power of minus R, I already got it, 0.21 times T. So this will go with this, so you have 1 over 2 equal to E to the power of minus 0.21 T. And then you will solve for the T, you will get that it is 3.3 years. So every time you need to get your depreciation factor first, then you find out what he wants. Then part B, what would 500 gram of this material be reduced in 10 years? So he wants to know the quantity after 10 years. So the initial quantity is 500 and the time is 10 years. So E to the power of minus R, I know, 0.21, and the time is 10 years. And then you will calculate this, you'll know the quantity after 10 years. Here he solved it, it's equal to 61.23 grams. Course practice question 1. The population of Canada doubles every 70 years. The population of Canada in 2012 was 35 million. Then what would be the population in 22? So my equation would be the population is equal to the initial population. So the initial population was 35 million. So this is 35. It is doubled, so 2 to the power of every 70 years. So here my denominator is 70, and he wants the population after how much time? It is 2012, and this is 22 minus 2012, 2 minus 20, 2 minus 1, that's 2, and then 0. So after 210 years. So this is how you fill your formula, which is the initial population. If doubles, so this will be 2. Every 70 years, so here will be 70, and then you will calculate the difference between the current year of this population and the future year that you want to calculate. So 210. 210 divided by 270 is 3, so this is 2 to the power of 3, which is 8 times 35, so it will be 280. Question 2. This is same as the activity in the ebook. A certain type of bacteria divides every 20 minutes to produce 2 bacteria. So to produce 2 bacteria, that means it is duplicated. So it is multiplying every 20 minutes. A certain colony started with 20 bacteria. So I'll start writing my equation. I started with 20 bacteria. It is doubling every 20 minutes. He wants how much after 10 hours. So after 10 hours, so this 10 hours I have to put it in terms of minutes, so it will be 10 times 60. Simplify, this will go with this. 10 times 6 is 60, so this will equal to 20 times 2 to the power of 60 over 2 is 30. He wanted 5 times 2 to the power of alpha, so this 20 is 5 times 4, and 4 is 2 to the power of 2 times 2 to the power of 30. Here you will add the powers, so it will be 5 times 2 to the power of 32. So your A or alpha, I cannot see, this is 32. 3. The amount of sodium present at any time is reduced, so this is reducing to half of its size in 15 hours. What would 1 kilogram of this material be reduced in 90 hours? So first I need to get the depreciation rate. So it is reduced to half of its size in 15 hours. So the Q final is going to be half Q initial, because after it is reduced to half of its size. So Q initial at any time t, which is after 15 hours in this case, so Q15 is equal to half Q initial. Okay, and my equation is Q at 15 is equal to my Q initial e to the power of minus R, which I need to calculate, times 15 hours. This will cancel this, so you have 1 over 2 is equal to e to the minus R and times 15. So I will take ln 0.5, it is equal to this number. So it will cancel this. This is equal to minus R times 15. So divide by minus 15. So this is your depreciation rate, 0.4. I will put it here. R is equal to 0.0462. Okay. So now what he wants what would be 1 kilogram. So my initial is 1 kilogram of this material be reduced in 90 hours. So e to the power of minus R is 0.0462 and 90 hours times 90. So I will solve this on my calculator. Minus 0.0462 times 90 is equal to this amount. Exponential is equal to this times 1,000. He said 1 kilogram and he wants the answer in grams. So times 1,000. So it is 15.6 and he wants to nearest gram, so it is 16 gram. Last question. Suppose that 500 milligram of this substance is reduced to 410 milligram in 1 week. Okay, so here he needs the answer in days and here he needs the answer in days. So let me follow days. Okay, so my amount, initial amount is 500 milligram. It is reduced to this much. It is reduced to 410 after 1 week. So e to the power of minus R times 7, because I have 1 week. So I will calculate how much is R. So 410 divided by 500. Shift ln answer, so and then divide by 7. The minus will cancel the minus, so this is your R. My R depreciation factor is 0.02835. okay, type here part A. What is the half-life of the this substance? Give your answer in days and to the nearest whole number. He wants half-life, so when it is going to happen. So the half-life, the final quantity will be half the initial quantity. So half Qi is equal to Qi e to the power of minus R, which I know, times T, which I need to get. So this will cancel this. So I will get ln 0.5. This is equal to R minus R times T. So my minus R, I will divide by minus 1. The minus will cancel the minus. So divided by R, which is 0.02835. So this is my time, 24.44. He said give your answer in a whole number, so this is not going to be rounded, so 24 days. So I'm solving here for the T. Part B. What would 500 milligram of this material, so my initial is 500 milligram, this is my initial, be reduced to in 30 days? Type. So I have the initial in 30 days, how much it will be, so he needs this. So e to the power of minus R times 30 days. So 30 days times R is this 0.02835, times minus 1, because I have a minus here,
exponential this number, it is equal to this times 500. You will get the final quantity will be 213.6, and he wants a whole number milligrams, so it will be 214. The 6 is going to be rounded, so the 3 will be 4, so your answer is going to be 214. To sum up this section, the population at any time t is equal to the initial population. If it is doubled, you will put 2. Every 20 days, 30 days, 70 days, this is going to be your denominator, and the time you will calculate between the initial year of this population and the final year that you want to calculate. So you'll put it t. For example, 2000 and 1000, so we'll put here 1000. 2000 minus 1000 is 1000. And the depreciation, so the quantity after time t is equal to the initial quantity that you started, exponential minus r, which is the depreciation factor, times t, the time that this substance takes to depreciate. So here, usually you will solve first to get the depreciation ratio. You will solve first to get the r, then you will solve back to get anything else.